Hi. So this talk was to together with Jakob, but unfortunately he's not here today. So I will just present
It's going to be
myself.
both of you, right? Perfect.
And so basically, it's based on a publication that we also presented last week at the IEEE Quantum Week. And the point here is that we are dealing with well-known problem on the classical space, which is the robustness, in particular adversarial robustness. And maybe I can guide you through the setting here. So we have like some data points in a high dimensional space, and usually we try to classify them. So in this case, we are just representing like a cluster so two cluster of the two data points with the confidence score of the network, right, associated to each point. And the problem is that on the classical setting, you have like curse of dimensionality, right? So when you have a high dimensional vector, the distance between two data points is very small, right? And what you can do with a neural network is that you perform like adversarial attack, right? So the adversarial attack is a manipulation of the input where it's based on a projection of your gradient back to the input space, right? And you can do actually with also the LLMs. So this is like a problem that has been around for the last 10 years. If you want to jailbreak an LLM, then you prompt, so you inject like a prompt into your input space, and you can ask for instruction to build like a chemical weapons or any other sort of things that you want to get out of the model. Right. So how do you deal with that on the classical setting? Is that you start doing like a sampling, for example, right? So it's one way. It's probably like the most scalable way that you can do for billions of parameters model, right? So you just compute like a distribution around the input. So in this case, it's just a Gaussian distribution. So you start counting how many times you hit the first class, how many times you hit the second class, and the ratio between the two classes give you like a certain stability guarantees. Usually it's an L2 norm in case of Gaussian distribution. If it's a uniform distribution, then you have stability in a L1 norm. And the problem with that is that on the classical setting, you need to sample a lot, right? So you need to take like more and more sample if you want to obtain like a good estimate of those boundaries, right? So for example, if you want to defend again just breaking attacks on the LLMs, you're smoothing your input, so you are just changing a bit some character, flipping some characters in your input sequence, in your text sequence, and then you're smoothing out the output. So the output will not anymore being able to change the actual prediction. And the same problem on the curse of dimensionality on the classical setting is appearing also in quantum machine learning. So as more as your Hilbert space is growing, more easy is to apply the same projection mechanism and change the output of the quantum neural network, right? So if we are considering, like a 10 years, 15 years scale when quantum machine learning will be available, which the same happen on classical machine learning. So we are talking about a system that has been started to develop like at a large scale 10, 15 years ago with the raising of the GPUs. We can start thinking nowadays, right, how to defend against like quantum machine learning models. And for this reason, I just want to bring like a common a good method that we saw from the literature and then we used as well. And this is like just like an overview of how it works, right? So this is like a quantum circuit. So you start by applying like a Grover search, basically. So you have like this gate UP, which is encoding like the input, the distribution of the input, so around your input, and then your quantum neural network, right? And with the Grover search, you're looking at into the distribution, how many times you are hitting the original class, so the class C in this case on the first qubits. And of course, we know that this does not scale super well with NISQ devices, right? So you have like an exponential term on the number of times that you want to estimate the phase of your quantum Fourier transform, and So what we did here is that, first of all, we look a bit better onto the different components of the circuits. And here we are just looking a bit inside into the first component, which is composed by like the input. You're embedding into the basis, right? You want to have a distribution on the amplitudes and embedding the input on the basis. So that means that you're representing all your states, if it's a Gaussian distribution or a uniform or other distribution. And in this case, on the right-hand side, instead, you're applying a Grover operator, right, which acts as an oracle. So basically, you're counting how many times you're hitting like the class Y. And in this case, you're just amplifying, right, in that distribution, the samples which are associated to the class Y. And there has been like some different works, right, in this domain that are using different distribution. Like the main one we also did like with the first paper on Winder et al. On 2023 was about applying depolarization noise on the amplitudes. So in this case, you can obtain like guarantees by smoothing like the distribution by using like the inherent noise of the system, right, which is depolarizing noise. And there has been other works on applying rotation gates to emulate like rotation noise as well. And the encoding strategy is different according to different methods, right? So you can embed your input into the amplitudes, into the rotational gates, or you can embed your input into the basis. The difference is that, of course, right, you have like different complexity on the usage of the qubits or the depth of the circuit, but also for the basis, you can exploit the fact that you have your input into the basis and then the distribution on the amplitude, right? And those are like the bottom-up work. So what we are looking at are bit flip noise, which are coming also from many sensor and devices. These are affecting like the, sorry, I just have to. So bit flip noise are affecting like devices and also time series, in particular for the project with Volkswagen. So how do we construct those bit flip noise distribution, right? So in particular, we have been looking at the K Hamming distance states. So in this case, you have like an input, and you want to see how many times you're flipping. So you want to constrain the flipping by just one Hamming distance away. So in this case, we have like, for example, an input of 0, 0, 0, then the flipping will be 1, 0, 0, 0, 1, 0, and 0, 0, 1, right? This is a bit different compared to the Dicking state preparation because it's input dependent. So the Hamming distance depends on the input X, while the Dicking states start always from the 0, 0 state, And here I'm just reusing the slide from the last conference, so it's a bit more technical. But in general, so what we are doing here is that we are trying to emulate the Hilbert representation, the Hamming distance. So what we are doing is that the probability here is just normalized through exponential decay, right? With the sigma, that is, you can control the decay of the distance, right? And then we are applying this into the amplitude of the state, right? So the x so in this case we are representing now the distribution where the k is dependent on the original input x, right? And it's a bit more clear from this slide here. In this way, we can use like a more compact version of the circuits instead of going through the amplitude encoding, so the Motolen state preparation, which will lead into a very large depth in terms of gates, right? And in this case, by using the sigma, as you can see, for example, for the state 0, 1, 1, we can tune up like the neighbor states, so those one Hamming distance away, which are the states 0, 0, 1, 0, 1, 0, and 1, 1, 1, right? And of course, this is not an exact representation of the distribution, otherwise we will end up with too many gates. So if you tune too much the exponent decay, then also states which are more than one Hamming distance away, they will raise up, right? So you need to find like a good balance for your decay. And this is coming from an intuition from the uniform distribution, which is the circuits on the right. And the uniform is just like applying like uniformly between neighbor state, like the same probability, right? And you can use it to obtain statistical guarantees on the model as well. And we are comparing here in terms of theory side, what will be the advantage. Sorry. What will be the advantage with 2 times the number of gates compared to the amplitude encoding, which is instead an exponential number of gates on the original circuits, right? On the Motolen state preparation, not on the additional sequence of preparation that they had in the follow-up works. The disadvantage here is that we use 2 times the number of qubits of the original circuits, but in the end, with the Grover search, we can definitely reduce by a quadratic factor the number of queries that we need to obtain on the model, right? And the disadvantage is the fact that we need to encode the system on the basis encoding, so that means that we are using a lot of qubits to perform, like to embed the input into a quantum circuit. So in the experimental analysis, we consider 2 data sets, like the iris, so the very common and small data set, and also a GAN point, which is a time series. In this case, the time series has to be discretized, right? So we have applied like words embedding, a bag of words representation. So basically, we are assigning like a letter for each different segment, which is 15 step. And a letter is just converted into a binary, so we are just considering like the first 4 letters and then assigning like a binary, 2 binaries for each letter. The accuracy, it's almost like 100% for the iris and 92% for GAN point, and the number of layers of the QNN, which is based on a basis encoding for the state, and then we have a strongly entangled layers later on. And if we just compare like from analytical, so from an empirical perspective, like the Q distribution, we see that in terms of certified robustness, so if we just sample from the QNN with like our state preparation and with the amplitude state preparation, which is an exact state preparation, we are close enough, right? So not exactly the same, right? But definitely in terms of gate state, in terms of gate number and depth of the circuits, which you care a lot when you're doing like something like Grover, you try to having like a very small and compact circuits, and that's what we have been obtained so far. And here we are comparing like, you know, a random sampling that you will have it, so you can perform like normally, or the quadro search, which is like this Grover search applied to the QNN with the input distribution. And in this case, we have a comparison for the same, for a quadratic difference, so 8 stand to a to the power of 2. So if we are looking at the top right, so the red curves, then we see that 50 is more or less close to 50 to the power of 2 for a 1 Hamming distance distribution or for a uniform distribution. Actually, for a 1 Hamming distance distribution, 50 it's equal to 12 to the power to the power of 2. But for the iris dataset, for the GAN point dataset, instead, we have that quadro with 120 shots for the 1 Hamming distribution is able to catch up with randomized smoothing, which will instead needs like 500 to the power of 2 shots to get the same estimation of the certified accuracy. And for the uniform, we are comparing the same. We haven't got like the most expensive one, but in general, so the 50 and 100 are already like in a good scale. So what's the takeaway from this study is that you can use like a K-Hamming distance state, which is an approximate representation of the distribution with a very compact number of gates. and it doesn't scale exponentially like the amplitude preparation, but just linearly, right? And you just need an additional 2 times the number of qubits. So that's the disadvantage. In the end, like, you know, Grover search performed like a quadratic improvement compared to the classical machine learning that we know, but it's not like a NISQ-friendly subroutine. So you definitely want to apply like some dimensionality reduction or the iterative quantum phase estimation. That is what we did. So instead of going through like, I think I have, instead of using like all the qubits for the quantum Fourier transform, what you did, what we did is that you just use one of them, and then you repeat for the m times the circuit. So for the last a0 to am times the circuit, and then you estimate the phase without the additional overhead of the qubits. Of course, if you use all of them, then you will have like you don't have to take m additional shot every time. And that's conclude the presentation. Thank you.